Okay, let's take a look at practice now 5. So the main idea we need here is similar triangles. But a related note is midpoint theorem. So let me just recap what is midpoint theorem. So if we have a triangle ABC and then we have a point X and a point Y, and then we have these two lines, right? In particular, a line connecting X to Y and a line connecting B to C. And midpoint theorem will say this. Okay, if we have X being a midpoint of AB, and we also have Y being midpoint of AC, and we also have XY parallel to BC, then we can conclude the following. The ratio of XY to BC must be 1:2 or half. Okay. Is it useful over here? Not really, huh? Not really. You just need similar triangles to do this question. So let me just erase the working I've written down previously. Okay, so this is the diagram. What the question is telling us is that T is a midpoint of CQ, right? So T is the midpoint of CQ, which means that we have a 1:1 ratio here. Okay, what else do we know? We know P is the midpoint of CA. So that means we also have a 1:1 ratio here. So this time I'm drawing square box. P is the midpoint of CA, but I'm drawing square box to remind myself that CP and CT both are 1 unit, but they are not equal. All right, one is long, one is short. What else do we know? We also know that, sorry, that's all they are giving us. Oh, right. So sorry, there's one more. They tell us that ART is a straight line and that TR is to RA, the ratio to be found is the ratio to be found. And sorry, to be shown to be 1:2. We need to show that the ratio here is 1 unit, ratio there is the ratio of the lengths here and there is 1:2 ratio. Now, you don't really need midpoint theorem for this question. Let me just go through this to show this TR is to RA equals 1:2. Let's see. So first thing, we need to identify that these two triangles are similar, right? So that means that the ratio here to here, 1:2, right? 1 unit versus 1 plus 1, 2 units, will be exactly equal to here to there, CQ to CB, also ratio 1:2. Which means that right now what we have, after we have proven CPQ similar to CAB, is that we have a ratio here, 2 units. This is 1, there will be 2, right? Okay, which means that if this is 2 units, what does it mean about this unit here? Must be 2 minus 1, so 1 unit. Here is 1 unit as well. But since this 1 unit represents one circle unit and another circle unit, that means that the ratio over here must be 2 circle units, right? Then if you look at this pair of triangles here, they are similar, right? TRQ is similar to TAB, which means that the ratio of TR is to TA must be the same as TQ is to TB, which has a ratio 1:3, right? If we know TR is to TA, the ratio is 1:3, we can clearly see that TA is made up of TR plus RA, right? TR plus RA. Which means that if we just, we know that TR is 1 unit, so that means that RA must be how many units? 3 minus 1, 2 units. So that means the ratio of TR is to RA is 1:2. Okay, and this is not a proper reasoning, not very algebraic, but that's the main idea. Now we go on to write it out formally. So first thing I prepared beforehand was this proof. We have used AA similarity test to show that triangle CPQ and CAB are similar. CPQ here, CAB there. The common angle at the top and a corresponding angle CPQ and CAB there. There. Corresponding angles because there's a F shape over here. And these two lines are parallel, PQ parallel to AB. Okay, from there we conclude that CQ is to CB, what I said previously, equals to CP over CA, which is a ratio 1:2. 1:1 plus 1, which is 2. Okay, and from there, CQ will be equals to half of CB, right? CQ equals to half of CB. So what can we conclude from CQ equal half of CB is that what is it? CQ is half of CB, but we know that CB is equals to CQ plus QB, right? So that means that QB must just be equals to CB minus away CQ, which is let's see. CB minus CQ, right? And CB minus half of CB, right? Because CQ is half CB, CQ is half CB. You can just substitute in here. Then CB minus half CB is just half of CB, right? So in this case, QB equals half times of CB. What can we conclude from that? If you look at the diagram, we realize that, oh, QB is half of CB. It's just saying the 1 unit to 2 unit ratio. This implies to us that CQ is to QB must be 1:1 ratio, right? Okay, good. So what else do we know? We know that CQ here is worth 2 units. So here must also be 2 units so that they can be the same, right? Okay, then let's just write it down this way. How should I put it? QB will be 2 times of TQ, right? QB will be 2 times of TQ. How should I prove that? I mean, maybe I can phrase it this way. QB is equals to half of CB, right? But half of CB is really just the same as CQ, since since we have it over here. And CQ is made up of CT plus TQ. But we know that TQ is a midpoint, so it's really just 2 copies of TQ, right? CT equals TQ, since T is midpoint. This is just really trying to say that this is 2 units compared to 1 unit here, 1:2 ratio. So QB is to TQ ratio is 1:2. But wait, what do we know about TB? TB is just made up of TQ plus QB. So it's just 1 unit plus 2 units, right? But if you want to write it up a bit more formally, you can rewrite it as TQ plus QB being 2 times of TQ. Where did I get this QB equals 2 times TQ from? From here. Okay, so that means we have TQ plus 2 times of TQ, which is 3 times of TQ. Right? TB equals 3 times of TQ. With that, we write down TB equals 3 times TQ. Sorry for the messy working. I'm bringing the working back over here to save some space. Then we conclude that TQ over TB must then be equals to 1/3, right? Just cross multiply a bit. Okay, then from there we conclude that, okay, here I'm not going to prove it, but by AA similarity test again, we can show that triangle TRQ is similar to triangle TAB. Now, if they are similar, we know that their ratios are equal. In other words, TR is to TA must be equals to TQ is to TB, which is 1/3, right? So TR is to TA has a ratio 1:3. Now, what do we actually need? We need, what is it? This guy, right? This guy, right? TR is to RA is 1:2. So if you zoom in on just this triangle here, we realize that the TR over TA, maybe I can rewrite it as TA over TR instead, which is equals 3/1. Then what else do we know about TA? TA is the long one, TR is the short one. So we can rewrite this TA as TR then plus RA, right? So let's just do that, TR plus RA. Numerator becomes TR plus RA, all over TR equals 3:1. We can always split this into two fractions like this, TR over TR plus RA over TR equals 3/1, which is just 3. But more importantly, TR over TR here, it becomes a 1. So 1 plus RA over TR. We're getting close. What was our objective again? We wanted TR is to RA equals 1:2. Let's just paste the goal over here. Can you see that they are very, very similar now? Then RA over TR must then be equal to 3 minus 1, which is 2. Or 2/1. Which implies that if you flip it around, TR over RA becomes 1:2, which means that TR is to RA has a ratio 1:2. And then we are done. Next question. I'd like to make a correction to the midpoint theorem here. This is wrongly stated. This XY parallel to BC condition should be a part of the conclusion, meaning that it should instead be something like this. Okay. If you're given the midpoints, then you conclude that the ratio is half and the two lines are parallel. Sorry for the confusion. Yeah. Okay, so let's begin this next one. So exercise 10C question 2. Ready? Let's go. So first thing, we realize that in order to prove that they are the PROF is a parallelogram, we need to show that we have opposite sides are parallel. Two pairs of parallel lines. In other words, PR parallel to OF, PR parallel to FO, as well as PF parallel to RO. Okay, that's our objective. And we can make use of midpoint theorem to help us to prove that. Okay, so midpoint theorem states that provided that you have a triangle, let's say A, B, C, and then you have X is a midpoint of AB, Y is a midpoint of AC, then you can conclude that XY is parallel to BC and XY is half of BC. Okay, so you need to be provided with midpoints, and your conclusion is that XY parallel BC, the bottom lines are parallel, the bottom of these two triangles are parallel, and also that XY over BC has a 1:2 ratio. Okay, so how can we use that to help us to prove this parallelogram? What we can do is to see that there is these two triangles that satisfies the midpoint theorem. Then therefore PR parallel to DU. And then you've turned your head 180 degrees and then you realize that these two triangles are also parallel. Sorry, are also similar triangles. So that means that you can conclude FO and DU are parallel. So if PR parallel to DU, FO in turn also parallel to DU, that means that PR must be parallel to FO. So you can do the same thing again, but this time with these two triangles. Conclude that PF parallel to QA. These two triangles conclude that RO parallel to QA. So PF parallel to QA, RO also parallel to QA. So therefore, we conclude that since they are both have a common parallel line, PF must be parallel to RO. So we have proven the two pairs of parallel sides, and therefore PROF is a parallelogram. Let's just write it out. So first step is triangle QPR and QDU. We can see that the P is midpoint of QD and R is midpoint of QU. So we can just quote midpoint theorem to speed things up a little bit. And we conclude that PR is parallel to DU. Next, we look at another pair of triangles. In this case, it will be AFO and ADU. It's the same working, it's just that this time it's F is the midpoint of AD. Midpoint of AD, and O is the midpoint of AU. This concludes that, and so we can quote midpoint theorem and conclude that by midpoint theorem, this time instead of PR parallel to DU, it would be FO parallel to DU. Okay, so let's call this 1 and call it 2. 1 and 2 combined together tells me that FO parallel to DU, DU parallel to PR, which means that FO parallel to PR, right? Very good. So we have our first pair of parallel lines. I'll call this a star. Then, okay, I'll just put an asterisk. Then next, we look at the other two triangles, these two triangles. Then later, these two triangles. So it's the exact same working again. So this time in triangle DFP and triangle D, what was that again? Is it A? I think it's A. DAQ. DAQ, we see that we have F is the midpoint of DA, and P is the midpoint of DQ. So again, we can conclude by midpoint theorem. What is it? PF parallel to QA, right? These two triangles, the base PQ parallel to QA. Sorry, PF parallel to QA. Actually, midpoint theorem doesn't just tell us that, it also tells us that, and what is it? PR equals to half of DU. What else? FO equals half of DU. What else? And also PF, sorry, I forgot to put an and. PF equals to half of QA, but that's not relevant to us, so I didn't write that down. I hope you understand. So this is number 3. And finally, let's go for the last one. So RUO and what's the other one? QUA, right? Let's just write it down. So in triangle RUO, last round already, and triangle QUA, R is the midpoint of QU, and O is the midpoint of UA. This implies that by midpoint theorem, the bases are parallel. So RO and QA. And RO is half of QA, or RO over QA equals to half. It's just a little bit more of algebra to bring the QA over. Yeah, so right, we look at number 3 and number 4. We realize RO parallel to QA. QA is parallel to PF, which means that RO is parallel to PF. Okay, so at the side we can write down 3 and 4 tells us that RO parallel to PF. Call it the second asterisk. Okay, so from the single asterisk and the double asterisk, we conclude that we have opposite pairs of uh, um, opposite pairs of sides being parallel, which means that the PROF is a parallelogram. Cool. Okay, that's it. Okay, question 2 done. Next question. Okay, let's take a look at practice now question 8. Okay, so you want to show that angle PXT equal to angle PQT in this diagram. You're given that XT is parallel to RQ. So let's just label PXT on the diagram first. PXT is where? Over here in black. Where else is PQT? PQT is here, over here in black. Why are they equal? Let's figure out. So first thing, parallel lines. What can you conclude? ZFC, alternate angles, corresponding angles, interior angles. More importantly, here is a F shape, right? So what can you conclude about this angle and this angle? They are equal, right? So that means this must be the black angle. Then now the question is, if this is equal to this, then why is that equal to that? This last part. So you think, and then eventually you realize that, oh, if you turn your head around, there's a circle, there's a tangent, there is this triangle here. There's this angle that is outside. Okay, there's this chord which is separating the circle into two halves, the major and the minor segment. There's an angle located at the minor segment, which means that this angle here must be the angle in the major segment, which is equal. Why? Because of alternate segment theorem. These two angles are in alternate segments. One is in the major segment, one is in the minor segment. Okay, so this angle equal because of alternate segment theorem. Maybe if I just draw a filtered version with just what is required to satisfy alternate segment theorem, it will look something like this. There's a tangent here, there's a triangle there, then there's this chord which is separating it. Maybe I just use a highlighter like this. Then there's the angle over at the side here and the angle over there. These two are equal. These two are equal because of alternate segment theorem. Okay, so yeah, we can just write up the proof now. So angle PXT is equal to angle PRQ. The reason for this is, I'll write it like this. The reason for this is corresponding angles. Then PRQ in turn is equals to PQT. This is because of alternate segment theorem. And then we are done. Okay, that's all for part 1. Okay, now for part 2, a bit more interesting. Let's take a look at part 2 now. Okay, let's take a look at this part 2. Our objective is to prove that angle PXT equals to angle QXT, right? So angle PXT equals to angle QXT. Where is QXT? Is over here. So we need to show that these two angles are equal. Sorry, I don't need the A here. Now, reviewed already. Okay, so from point T, sorry, there is a circle, right? This circle here that passes through the 4 points P, X, Q, and T. Now, this is possible because we have already proven previously that what are the two angles? PXT and PQT are equal, right? So let's just color it in black again like this. So these two angles are equal because of angles in the same segment. You can think of it that way once you have drawn the circle. They both are produced from the same chord PT, right? Angle PXT and angle PQT. Right, so this is to be proven. Let me just write that down, to prove. Now, first thing you need to realize is that we have yet to use the fact that these two are tangents. In particular, this is an ice cream cone. This is an ice cream cone, tangents from external point. In other words, this length and this length are equal. PT equals to TQ. So let's just write that down first. PT equals to TQ, tangents from external point. Now, what's so special about an okay, if you pause a while and you take a look at the diagram, you realize PT and QT are equal in length, which means that, hey, there's a triangle here. What kind of triangle is this? Isosceles triangle, all right? So that means that we have, what is it? Base angles are equal. Okay, so we can conclude from there that these two angles are equal. Okay, fine. So what? So very good already. That means that this angle here will also be the black color angle. And we are essentially done, because can you see that these two angles are actually equal? Why? Because angles in the same segment again. So therefore, we can go from here to here. That's from part one. From here to here, that's because of isosceles triangle base angles of an isosceles triangle are equal. And then from here to here, that's because angles in the same segment. And then we are done. Now you just need to write it up. So angle, okay, sorry, let me just write down. This implies triangle PQT is isosceles. Since it's isosceles, what can we conclude? This implies that angle PQT is equals to angle QPT. Okay, so let's just write it out from the top. We want to show that angle PXT eventually equals to angle QXT, right? So let's start from PXT. So PXT we know is equals to angle PQT. Reason, from part one. Or you could also say angles in same segment, since we already know that there is a circle here, right? PXT, PQT, they are equal because of angles in same segment. It's also another possible reason. Now for PQT onwards, we realize, from the previous part about isosceles triangle, let's just call it number one here. Therefore, we conclude angle PQT equals to angle QPT, base angles of isosceles triangle. Okay, I can just put down one here. Maybe I should have placed the reason at the side, base angles of isosceles triangle, like this. Good. So that's angle QPT. But are we done yet? No, one more step. QPT equals to the pink angle we are trying to find, QXT. Reason? Reason is angles in same segment. Okay, good. And then we are done.